Um, so let me just briefly recap what it is that we did last time. So I'm going to start off sort of a little bit into this, actually into the second lecture. So in the second lecture, I introduced sort of an algebraic setup in which we can view the signature. So this was this space of formal series in D non-commuting determinants. The purpose of me doing so was that we had a very convenient way of writing Chen's identity. So we could write Chen's identity as in this very kind of compact way, without necessarily referencing words. So this product that we saw in this space of formal series was kind of somehow intertwined very nicely with splitting up an interval into separate chunks. So we saw that one of the main applications of this was that allowed us to compute the signature of a piecewise linear path in a very efficient way, without ever actually needing to sort of, we performed the integral in order to calculate what the signature of a straight line was. This was this exercise. So we saw that the signature of a straight line was like a kind of an analog of the exponential. And then Chen's identity allows us to glue all of these pieces together. So this is the signature of a piecewise linear path. And this is essentially how you compute the signature in practice. Okay. Okay, so I will briefly skip over these parts here. There's this time reversion, and we saw that the kernel of the signature map contained this certain quite natural, well, it contained these tree-like paths. Okay, so I started off in the third lecture by kind of backtracking a little bit and giving some explicit computations in the space of formal series. So I've also actually updated the so if you go on Sococo into the room for these lectures, you will find an updated link for the slides. So I've updated the slides on my own webpage. So if you want to see an updated version of these slides, go to Sococo and you'll find the link there. Okay, so yes, we saw how to make these computations, and something that was quite interesting was that so maybe I'll just go to the slide, was that basically an arbitrary power series of elements in this space of formal series made sense, provided that the zeroth coefficient, or the empty set coefficient of the element x that we're looking at, is 0. So provided that sort of this x empty set is equal to 0, an arbitrary power series of this type always made sense as an element of the space of formal series. Okay, so this allowed us then to define the so-called log signature as a power series to do with the usual signature. And I tried to emphasize that this was a set of independent features. So there's no generic, unless some miracles happen, there's no way of kind of matching up terms of this log signature with other terms of the log signature, unlike with the classical signature due to the shuffle product. Oh yes, and Oli has posted an updated version of the slides also on the chat, so they're available directly there. Thank you. Okay, so we saw that this log signature also had some nice algebraic properties. It took space in this in a linear space now, so the signature took place in a nonlinear group, and now the log signature takes values in a linear space called the Lie series. And we saw how this kind of connected with the classical Campbell-Baker-Hausdorff formulas. This was quite, which is actually also helpful for computations, because you can actually compute the log signature directly without necessarily having to compute the signature itself. Okay, so now I see my slides are not rendering again, but that's fine. And then the kind of the bulk of the previous lecture was we were looking at these at the way of how to move from data to path. So we saw that it was a two-step process. So first you wanted, if your time series takes values in an arbitrary set, you usually want to apply a feature map in order to map this set into a vector space, which for us at the moment, at least, it's RD. So we get an RD value time series. And then from there, you can create a continuous path using, say, piecewise linear interpolation. And from there, you can compute the signature. So after actually creating the path, you typically also want to perform some transformations in the path before you compute the signature. So motivations for this was that you want to capture time parameterization, or that sometimes your time series, so there's plenty of one-dimensional time series that are very interesting to study. And so you'd like to apply the signature method there. So you need to increase the dimension of your path in order to do so, because signatures of one-dimensional path only capture increments. Okay, so we looked at the so-called time augmentation method of doing this, and also at adding lags. So adding lags is, I said before, was a classical sort of time series analysis consideration. So I've added a reference here as well. Okay, so then so at the end of the last lecture, and what I want to speak about in this lecture is how to move from the final step of this pipeline that I described, of moving from signatures to learning algorithms. So the role of the signature here, let me recap, is that it acts essentially as a robust data compression method. So it retains a lot of the important features of your path, but in a much more compact way. And a large variety of learning algorithms can then be applied once you extract these signature features. So essentially, because these signature features are a vector, once you take a finite number of them, you can apply any learning algorithm that works with vectors. And I wanted to focus on a particular example of this, so a situation where actually this interaction between the signatures and learning algorithms is, I think, quite a little bit rich. And this is with kernel methods. Kernel methods operate by starting off with a finite collection of samples. Which take values in a potentially nonlinear space. So let me emphasize that this is sort of an arbitrary set at this stage. And we need to find a kernel, or sometimes we're given a kernel, sometimes we need to design a kernel, which is, for us, it's going to be a symmetric positive definite function on the space. So that means that this matrix is positive definite. So all choices of xi and xj. So there's a number of machine learning algorithms that operate with these, just with these inner products, and not necessarily with the samples themselves. So you kind of use the samples to create this big matrix, and then there's a number of ways of kind of learning these of extracting information from the data just from this matrix. Okay, so then I gave a heuristic way of connecting this with the feature embedding picture that I presented before. So essentially what kernels, the reason that they work and what they allow us to do is that they embed your space X, which is potentially a nonlinear space. Like you can think of this even as the space of graphs as a concrete example, or an alphabet. And it embeds it into a large vector space, potentially infinite dimensional. So this vector space is called the reproducing kernel Hilbert space of a kernel. So the feature map was this map here. And so for example, it would embed R if we use this so-called Laplace kernel into H1, but in a nonlinear way. So R is of course a linear space, but in this particular case, we're forgetting the linear structure of R, and we're just kind of embedding it into H1 according to this kernel. Okay, so this is where we left off last time. Let me just get a clock to keep track of time. Okay, so let me move on to how we apply the signature method for how we can combine signatures with kernels. So we're going to introduce. So I'm going to follow what I think is quite a nice work. This is due to Franz Corelli and Harold Oberhauser. So they introduced a particular kernel on the space of paths using the signature. So the way that you define this this kernel is you fix a truncation level m, which is a finite truncation level, and you compute the signature to level m. So you compute the signature for all words of length less than or equal to m. So I'm going to denote this by kappa m. There's another kind of suggestive notation is this inner product type notation, but explicitly it's just the sum over all words where you take the products over these signature terms. Okay, so a couple of remarks about this definition. So taking m strictly smaller than infinity, so that this is a finite sum, ensures, first of all, it makes this whole thing computable, and secondly, it helps with overfitting. So in case you somehow had a way of computing this big infinite sum, using maybe some analytic methods, you might not always want to do so because this means that you have a lot of it's a bit like using too many features in linear regression. You might be subject to overfitting. Okay, and then also the fact that we restrict to m being finite, and also the fact that signatures don't actually determine paths. This kernel on a space of at least parameterized paths is not strictly positive definite. It's only positive semi-definite. And there is a way of turning it actually into a positive definite kernel by taking, so you would take m is equal to infinity, so that this would become an infinite sum, and then you would kind of appropriately mod out the space of paths either by tree-like equivalence, or you would add time and mod out by translations or something like this. So there's just there is a way to make this kernel positive definite if we wanted to, which may be very helpful for theoretical purposes. Okay, so let me move on to, okay, so actually, let me actually just mention the final thing. So just, although this kernel is not positive definite, in applications, this is not often crucial. So this Moore-Aranjan theorem doesn't hold for positive semi-definite kernels. You don't have an injection in general. It's going to be just a map. But that doesn't stop you from actually, in practice, you often have this the case. You want to apply kernel learning algorithms without a positive definite kernel. So semi-definite is often enough. So this is going to be the case for us. We're going to be happy with a semi-definite kernel. Okay, so let me present now actually what was in some sense the main insight of this work that they did. It turns out that you can actually compute this signature kernel in a very efficient way. So I actually previously said that what we do is we compute the signatures and then take the sum over all of these words. So it turns out that you don't actually need to do that. Turns out that in order to compute this kernel, you don't ever need to compute the signature itself. So this is called a Horner scheme. So it's Horner schemes are kind of better known for polynomials, and essentially they speed up. You kind of write a recursive it's a recursive scheme that allows you to compute polynomials without having necessarily to compute like x to the 7 and then x to the 8 all separately. So it speeds up these computations. And so just like for the classical Horner scheme, there's a Horner scheme for signatures. So you can compute the inner products of signatures in a recursive way without ever actually needing to compute the signatures themselves. And the running time actually for say for piecewise linear paths I will present on the next slide. So let's just see the kind of the mathematical statement first. So consider two paths x and y. And then for two times s and t in the interval AB, and our some truncation level m, which is non-negative, we're going to define a time-dependent version of the kernel that I just presented. So it looks exactly the same as it was before. It's just that it's indexed by s and t. And the first signature I take not from A to B. So if you remember on the previous slide, here I took from A to B in both signatures. Here I'm going to take kind of essentially restrict my path x to the interval A to S, and the path y to the interval A to T. So for this definition. So I'm going to look at AS and AT here. And so explicitly it's given by these two, by this sum. Okay, and then what the recursive formula tells us is that in order to go from level m from truncation level m to truncation level m plus 1, I just need to compute an integral. And this integral is a two-dimensional integral. So I again restrict the time st here, and essentially if I think about it as a plot like this, so it's this is A, B, this is A, B like this. Then for every point in time st, I'm going to this integral takes this is s and this is t. Then this integral takes is over this domain, and I'm going to integrate this previous kernel over this domain against this this kind of two-dimensional measure. So this two-dimensional measure, so this is nothing but a fancy way or a compact way of writing. So this is just a compact way of writing sum over I1 to D of x dot ui y dot vi du dv. So if you like, this is a signed measure, absolutely continuous with respect to the Lebesgue measure on the square. And I'm going to be integrating all the previous values on the previous level, on level m, against this measure of this sort of time-dependent kernel. And so this gives me the value of the kernel at this point st. Okay, and so so probably I could even leave this the proof of this as an exercise. It's actually very straightforward. I think it's a very nice remark, but the proof is very straightforward. I've included it here for completeness. So so I first just written out the definition again, and then I apply the definition of the signature, the recursive definition. So for I, the length of I is equal to 0, the only word is the empty word. So, and the value of the signatures is 1. So this gives us this term here. And then the rest of them, I've put them into the sum. So I equal to 1. This is this sum over here. Okay, and then I've just used the definition of the signatures. And then all that we do is we apply for Beanie. So this is now a product of integrals. So I can write this out as a product, as an integral over the product space. And so the domain of integration is this integral a to s a to t, which is the same as this one here. And then kind of lo and behold, if you combine these sums with these terms over here, you'll notice that this is precisely the definition of this kernel here. And this sum I is equal to 1 to d was this the sum that appeared in the notation that I kind of hid in this dxu dyu dyd. So the sum combined with this final integrand term is the same as what I wrote in a few slides ago. Okay, so this is a kind of a very simple thing to prove. It's quite straightforward, but it has quite a remarkable consequence. So this consequence is that, as I mentioned before, to compute the signature, the truncated signature at level m, we actually never need to compute the signature separately. We only need to inductively perform these integrations over these squares. So inductively need to compute these all of these guys for all s and t and for all k between 0 and m. Okay, so then kind of the main consequence of this in terms of computability is that for piecewise linear paths x and y with L linear intervals, so if there are L subintervals over which they are linear, one can very efficiently approximate this inner product. so not exactly compute it. Computing it exactly is still a little bit tricky, but you can very efficiently approximate it using O L squared m time and O L squared memory. Let me just briefly say that the way this approximation works is that, okay, so if you think about the square again, so AB, and say that we have L intervals of time over which our curves are linear, then on each one of these squares, so draw them in green. So over each one of these squares, this term x dot u y dot v, it's so I say sum over I. On each one of these squares, this kind of Radon-Nikodym derivative with respect to the Lebesgue measure is constant. So in each one of these blocks, this term that appeared in the previous recursion, in this recursion here, this is constant. So in each one of these squares, the measure against which we're integrating is a constant with respect to the Lebesgue measure. So the unfortunate thing is that the kernel itself, though, kind of changes values according to this sort of as you move along the square. But you can essentially just say that, okay, I'm going to approximate this kernel just by using the sort of inside of that big integral that I had before over all of these squares. I'm just going to restrict it to the value on the bottom left square. So I'm going to also enforce that this kappa it remains constant over that square. So this is how this approximation works. And so this is kind of like how you would approximate a two-dimensional integral using like a rectangular mesh. So it's not exactly the value of this kernel, but it's very close to it. And you can find an explicit error in the difference. Okay, so this is the way that this approximation works. So then what we should do is we should compare this to kind of the more naive method of first computing the signature and then taking this inner product, this sum over the words. Well, to compute the signature, to level m, say, there are the number of words at level m is d to the m. So the number of the cardinality of I in the words that have length m, this is equal to d to the m. So just to even write down the signature at level m, we need d to the m kind of bits of memory somehow. So we need, or even more, because there'll be floats or something like this. So writing down the signature even takes a lot of time. And we notice that there's no dependence on D. So the dependence on D is actually hidden in computing the inner products. So maybe if computing the inner product between two, so the inner product being kind of this inner product x and y or something like this. So it's inner product of two vectors. So if computing this takes some fixed amount of time, then you would multiply this whole thing by that amount of time. But this certainly doesn't scale exponentially in the dimension. So there's a really large reduction in computational complexity if you perform this computation recursively rather than computing the signatures first. There is a small trade-off in that you have an L squared computation here versus just an L over here. So if you're working with really long paths, then and you didn't want to compute a signature to a very high level, then actually there still could be an advantage in computing this kind of direct naive method. So maybe if D is quite low, if it's a two-dimensional path and you're only interested in level 5, but the length is 10,000, then perhaps computing the signature directly would still be more beneficial. But especially in higher dimensions, it's infeasible to compute the signature to anything but level 2, or say level 3 maybe. Okay, so this is quite a nice method of computing these inner products. Yeah, so as I mentioned, this OL squared time really just comes from computing inner products, essentially these finite differences, which are relatively quick to do. So as I said before, if the inner products are cheap to compute, then the algorithm is completely dimension independent. In fact, you can even feed into the algorithm as input, not the actual time series x and y, but these kind of inner products of these intervals, of these increments. So if you do that, then the whole algorithm just runs without ever caring about the dimension. Yes, and then so the approximation error in this statement can also be made quite explicit. And by taking L to infinity, so by treating because a piecewise linear path with L linear intervals is also a piecewise linear path with L+1 linear intervals. You just kind of arbitrarily divide one of the intervals into two pieces, and it's still piecewise linear over those subintervals. So by taking L to infinity, you can send the error in this approximation to 0, also in a dimension independent way. Okay, so let me move a little bit up one level in complexity. So the whole entire algorithm worked with these inner products between increments of paths. So an important remark is that what this means is that if we're given some sort of a positive definite kernel on our base space X, so remember here again, I want to emphasize X is an arbitrary set in which our sort of time series takes values. So in the previous algorithm that we looked at, we restricted attention to RD and to this to the Euclidean inner product. So we can replace RD by the set X and some positive definite symmetric kernel K. And then we have this space H, which is the reproducing kernel Hilbert space, of kappa, as well as the embedding of X into the Hilbert space. Yes. So what this allows us to do is then we can use this embedding as the feature map that I mentioned right at the beginning of when we talked about data to path. So if we're given an X-valued sequence, little xi, then we can define an H-valued sequence, which is this capital Xi, by kind of applying this map X to kappa X. Yes, so and once we have the sequence, then we can build a continuous path from it. So say, again, just by piecewise linear interpolation. So now this path X is really a path from, so it's a bounded variation path from AB into this reproducing kernel Hilbert space, potentially infinite dimensional. So if our kernel here would happen to be this Laplace kernel or a Gaussian kernel, then and X, so X in this case would again be RD, but we forget its Euclidean structure. Then these Hilbert spaces become infinite dimensional. So this is now a path which potentially takes values in an infinite dimensional space. So yeah. So I only ever spoke about signatures in the context of RD, but I hope at this stage you can sort of take my word that actually signatures still make sense in infinite dimensions, provided that the target space is, say, a Hilbert space. And it works actually for quite general Banach spaces, but if it's a Hilbert space, you can just use an orthonormal basis to sort of compute everything. So signatures, so for a path of this type, S of X still makes perfect sense. So the words I here would be kind of over an infinite alphabet, if you like, rather than just the alphabet 1 to D. Okay, so it still makes sense to consider kernels of these guys. So this is an extension of this algorithm or the running time theorem that I had before. So suppose that for two elements, little x and little y, computing this kernel kappa xy takes some c amount of time to evaluate. Then if we take x-valued sequences, xi and yi, then we build the paths capital X and capital Y according to this third bullet point up here, this one here. Then we can so this level M signature kernel still makes sense. You can still compute these inner products. In fact, the exact expression is given by, so the mathematically correct expression is this. You sum over all the levels from k is equal to 0 to m, and sort of the correct interpretation is that now these signatures takes values in h tensors itself k times. So the exact meaning of this is not sort of so important. If it's familiar, then that's great. If not, it's just kind of like think of this as the vector space spanned by words of length k in some orthonormal basis of h. Yeah, and then so this has a natural inner product structure, and so these you can take the inner product of these to the kth levels of these signatures. This is what I now call this signature kernel. So this is what I previously called kappa m of x and y. Right, so this kind of still makes sense. This is a generalization of the finite dimensional setting that we were in before. And the computation takes essentially the same amount of time as it did in the finite dimensional case. So this is an example of this, the fact that these computations are completely dimension independent, provided that these kernels are cheap to evaluate. So essentially previously we had an L squared times M, and now I just add this C, which is the computation of the kernel. And it takes OL squared memory as before. Okay. So, so what I wanted to emphasize here is that these paths, so capital X, capital Y, they can take values in genuinely infinite dimensional spaces. So it makes perfect sense to do this this procedure for, say, the Laplace kernel on RD. So if you have a path in RD, you can essentially what you're doing is you're lifting it to the reproducing kernel Hilbert space. By embedding it through this kernel feature map. And so now this is a path in some infinite dimensional vector space. And of course, you can't write down the signature of that because it's really a path in some infinite dimensional space. It has you'll need an infinite number of coordinates to write it down. But the remarkable thing is that you can still compute the inner product of two of these signatures together. That's just a real number. So given two paths in RD, X and Y, when you lift that to the, or I guess here I'm calling it little x, little y, when you lift them up to the big reproducing kernel Hilbert space, capital X, capital Y, you can compute the signatures of those guys there and take their inner product. And this is, there is a signature for those guys there, and then you can compute their inner product using this recursive formulation. So I think this is quite a nice way of thinking about signatures in infinite dimensional spaces as well. So signatures in infinite dimensional spaces actually are of kind of computationally tractable and can be important for applications. Okay, so I'm going to now, I'll present very briefly what Karel and Oberhauser has found, and then I'll speak about my own work with Harold on this topic as well. The motivation of Karel and Oberhauser for this was that they wanted to apply this to classification problems. So they looked at both the Euclidean and Gaussian signature kernels. So the Euclidean one is the very first one that I presented. This was when the classical signature in a product. And then they compared it to this more kind of exotic one where the paths actually take values in infinite dimensional spaces by using a Gaussian kernel. And they looked at a support vector classifier and applied it to hand movement and hand digits classification. So so I think at least for one of these experiments, they compared the Euclidean and Gaussian kernels and actually found that the Gaussian kernel really outperformed this the Euclidean kernel. So the case in which you just stick with the Euclidean in a product. So kind of injecting your time series into this infinite dimensional space and computing inner products there it created a lot more. It was somehow a much more descriptive operation of the time series. So it captured a lot more information. So perhaps for people familiar with kernel learning, this is not so surprising because a lot of kernels, like this picture of injecting your space into an infinite dimensional vector space is quite familiar. This is the whole point of using kernels, that you can computationally work with infinite dimensional spaces. Okay, so let me just so in the last 20 minutes, I want to just present what Harold and I did in this direction. So later, a few years after this work, we used this idea of kernels as well as expected values of signatures to introduce a metric on probability measures of paths. So our main motivation was actually theoretical, but we applied it later to a computational problem. So this metric, so given two probability measures on paths P and Q, we define the square of this metric as being essentially the difference between the expected values of their signatures squared. So this difference is comes from this inner product that we put on the space of tensor series. So one can show that this, provided that your probability measures are sufficiently well behaved, this gives you an actual metric on them. And because this norm here is given by an inner product, you can this kappa now is the kappa on the signature. So here kappa x and y, down here. So this is equal to the sum over all words essentially. So where we don't restrict to finite. You can use the structure of the norm that it comes from an inner product to simplify this difference into an expression of this type. It's called the reproducing kernel property. And this is not our observation. This is actually quite a classical thing in kernel learning. It's called a maximum mean discrepancy. So you can use kernels to define metrics on probability measures. And because they come from a kernel, they have this very nice formula in terms of expectations. So here, x and x bar are two independent copies sampled from P, and y and y bar are two independent copies sampled from Q. Where, as I said before, P and Q are probability measures on paths. Yes, so this makes it, this final expression with the expectations means that it can actually be, that it's computable, or it can be approximated well. So our motivation for this was primarily theoretical, but we noticed that it had quite a nice application to two-sample hypothesis testing. So this was the very first problem that I motivated this mini course with. So the two-sample hypothesis test was the goal of it was to test the null hypothesis, which is that two probability measures are equal, versus the alternative hypothesis, which is that they're not equal. And you want to decide to either reject or accept the null hypothesis given a finite number of samples from P and Q. Okay. So again, using kernel methods for two-sample hypothesis testing was not our idea. It was actually done in quite a systematic way back in 2012. There's quite a nice paper about this called kernel two-sample test. Okay, so here I've rewritten the problem. Given a finite number of samples from P and Q, we want to test the hypothesis H0 that they're equal versus the alternative that H1 that they're not equal. So the strategy now is that we want to, so we have this metric in hand, this metric dpq. And because it was given by this formula with the expectations, this means that we can actually estimate these expectations using samples. So common way is to use an unbiased estimator. So this in this paper that I mentioned before, they propose quite a nice unbiased estimator, which is this statistic t²u. So it's just similar to how you compute variances. And then the strategy is that you reject H0 if this test statistic TU is large. And the way that you determine what large in this case means is up to you. So so what we actually used was a permutation test statistic. but you can also use some sort of parametric, non-parametric lower bound on it. So there was so again, in this paper, they kind of also provided a kind of a value. So okay, there's this, okay, it doesn't look like anything at this moment, but it's some number that as n goes to infinity, this number goes to 0. And if this test statistic is bigger than the C alpha, then you get you get a test with whose type 1 error is bounded above by alpha. So this is called the kind of the confidence of the test. And it's bounded above by alpha, regardless of what P and Q are. So the type 1 error is the probability of rejecting a true null hypothesis. So if P and Q are actually equal, it doesn't matter what they are, then by following this procedure of rejecting H naught whenever T squared is bigger than C alpha, you're guaranteed that no matter what your kind of no matter what the probability measures are, your probability of making a type 1 error is not going to be bigger than alpha. Okay, so the exact kind of hypothesis test that so the data that we applied this to is a combination of real and synthetic data. So we took 30 families of time series from quite a well-known multidimensional time series archive, the UEA, available at the link down below. And so this time series comes from a bunch of different fields. So one of them is this worm movement. You kind of track the movement of a worm and different parts of its body. Another one is phoneme audio recordings, where you track how, I guess in this case it would be the pitch or something like this of a voice, the loudness as well. So the point is that from this time series, you might want to classify whether what you're hearing is a sh or a ch or a ts sound, something like this. Okay, so these time series come from a wide family of fields. And then we kind of turned them partly into synthetic data. So what we did is we truncated each time series after L steps. So we looked at the first L parts of this time series. And we created P and Q as follows. So P was that we sampled W uniformly at random from each one of these families. So each one of these families contains a huge number of time series. We just sampled one of these time series uniformly at random, and we doubled its length. So we we concatenated it one after the other. This gave us a sequence of length 2L. Okay, so that's not very helpful. So what we did for Q was that we did the same exact thing. So okay, so for Q, we need to distinguish between whether we're working under the null hypothesis or under the alternative hypothesis. Of course, under the null hypothesis, we just said Q is equal to P, because that is the null hypothesis. And under H1, so when they were not different, when they were not the same, we let X be distributed according to Q by saying that X was equal to W1, WL, and then we swapped the order. So we concatenated it as before, but in doing so, we swapped the order of the time series. So in each case, we created so P and Q are now essentially probability measures on sequences, which we treat as paths. P is always kind of this repeated time series. And Q, when it's not equal to P, is a flipped time series. So it's sort of like it's a mirror version of itself. Okay, so this is a little bit synthetic, but we need to somehow generate samples from P and Q. So we chose this method. So despite actually it's a very simplistic setup, this is actually quite. It turned out that this experiment had quite rich results. So we combined this. So what we did was we combined this MMD from the signature that I described before, this maximum mean discrepancy, with a permutation test statistic. So at this stage, it doesn't there was some way for us to tell what this test statistic or what an estimate of this metric was, and when it was larger than what you would expect. Also with this unbiased estimator that I presented before. And we benchmarked this, so we compared this against other maximum mean discrepancies that came from standard kernels, as well as classical test statistics that didn't come from kernels. So the ones that we used were called the Wolfowitz test and the Hotelling t-test. Again, the details behind this is sort of not important. It's just a test that tells you essentially when you should or shouldn't reject a null hypothesis. So the type 1 error, okay, we capped this at 5%, at least asymptotically as the sample size increased. And what we were interested in was measuring the how far how small could we make the type 2 error? Because you can always create a test which is sort of like I'm never going to reject the null hypothesis. In this case, your probability of making a type 1 error is 0. But then your type 2 error could potentially be very large. In fact, it will be 1, because you will never distinguish between P and Q. So you always want to balance between these two guys. And so typically you would cap the type 1 error uniformly over the probability measures at some scale, like 5%. And then you would measure what the probability of the type 2 error is. And the lower this probability, or the larger 1 minus that probability, the better your test is, the more discriminative your test is. So this is called the power of the test. So the closer to 1, this is the better. So we empirically measured these things. We got the following results. So I should mention actually these results that I presented, they're not actually yet on the archive. It's still sort of partly in progress, but they're partly committed on a repository of Java Toth called GPSig. So I've collected a sample of these time series. Remember, there were 30 of them. I guess I've put in nine samples here, so in the first, so this is just the name of the time series. It doesn't really matter what the name is here. This is the dimension of the time series. So you can sort of see that these time series vary in dimension significantly. So some of them are quite low dimensional. There are some which are 2, 3 dimensional, but then the highest dimension was 1,345. These are very, very high dimensional time series. So computing the signature to level 3 of this guy would already be extremely difficult, for example. Or applying, in fact, applying any method to such a high dimensional time series is very challenging. So, so the classical MMDs that we compared to were Euclidean, Gaussian, and Laplace. And what I mean by the classical MMDs is that we just took this time series and we treated it as a big vector. And then we applied, so we treated this as a big vector in R times sort of R times D times L. So it was a vector in the space, and then we just used the Gaussian kernel on the space, or this Euclidean kernel on this big vector space. You can see that for for most tests, these classical MMDs, they performed very poorly. So they only ever matched up to the Euclidean, to the signature kernels in one of the tests, where in fact all of them performed equally badly. And maybe in the other samples, there's also a couple of other ones that, but I don't think there was a significant difference between. There was never a case where the classical MMD significantly outperformed the Euclidean signature kernel. So yeah, so in this column, I looked at I presented the Euclidean signature kernel. So we also actually looked at the Gaussian and the Laplacian signature kernel, so the one that I presented at this sort of like a little bit higher level of complexity case. And in some cases, they perform better, but actually surprisingly for us, in contrast to the classification problems that I discussed before, like this hand movement classification, in this hypothesis test setting, the Euclidean signature kernel in general performed better than the nonlinear kernels, than the Gaussian and the Laplace kernel. And it's also maybe worth pointing out that actually the kind of usually the optimal, so we optimize over the truncation level. So the truncation level is a hyperparameter. So because the kernel typically comes with this truncation parameter I. Truncation parameter M, sorry. So this truncation parameter M is something that you should optimize over. So when we optimized over it, we found that it typically was sort of like level 5, perhaps, or sometimes a bit lower, like maybe 4 or 3. So so it's not like you need to look at extremely high levels of the truncation level to get quite a discriminative test. But also you shouldn't just be looking at the increment or just level 2. You kind of need to look a little bit higher, level 4 or 5. And then in this final column, there was this Hotelling and Wolfowitz test that performed actually, they performed quite well whenever they were applicable. But here I don't even collect, I didn't even present their results because we couldn't get a computer strong enough to run these tests on such high dimensions. So these classical statistics, they scaled very poorly with the dimension. Whereas the Euclidean signature kernel scaled, it performed equally well in the low dimensional, or the running time was the same in the low dimensional time series as it was for the high dimensional time series. So I think these were quite interesting results that we found. At least we were quite surprised by them. Okay, so I see that my time is actually completely up. I've included a final slide just in case I had time on kind of like to end talks with maybe some further research directions. So maybe if it's okay, I'll take just 1 or 2 minutes to describe these. Let me just show them all here. So the first one is there's an analog of signatures called branch signatures. And these are much closer in spirit to classical numerical analysis methods, such as Butcher series. And they're very much like signatures. They're defined using integrals, except they're not indexed by words, they're indexed by certain rooted trees. And the interest in them is that they provide a much more convenient framework for dealing with discontinuous processes. And also for processes that don't respect the classical chain rule. So for example, semi-martingales. So extending kind of these things with all the things with the classical signature that are presented to branch signatures, I don't believe should pose somehow a fundamental problem. I think that it should be certainly doable. And it would be quite interesting to compare whether these branch signatures confer some sort of significant benefit and why. Understanding why, if they do, would be important as well. So for example, there's a reason Butcher series work with trees rather than with words, because somehow trees encapsulate information better. Also extending from so most of the stuff that I presented was unparametric, so it worked for arbitrary probability measures. Sometimes understanding how to use domain-specific knowledge, for example, knowing that your probability measure is a semi-martingale, could be interesting. Also, how to sort of integrate the signatures with learning algorithms beyond this standard pipeline, beyond just using the signature as a feature in a learning algorithm, would also, I think, be quite an interesting direction. So in this direction, there's this paper that I give here, where these authors use combine signatures with neural networks, but not in the way of just feeding the signature as a feature into a neural network. And then one of the other big questions in this direction is how to properly extend the signature method beyond time-ordered data, and whether that's even possible. So, is there some sort of analog of higher dimensional signatures? Maybe some people know that there's a theory of regularity structures which extends rough path theory, and maybe some ideas from there can be helpful in this direction as well. So I have advertising a small work that I did in this direction very recently with two collaborators from Bath, Hendrik Weber and Andreas Gerasimovich. So we definitely don't provide a complete answer to this problem here, but we kind of just want to show that there's maybe something to look at in this direction. So I think this would be sort of extending beyond time-ordered data would be a very interesting direction. Okay, so I'm already a few minutes over time, so I would like to thank you for following this course and for your attention.